Hello everyone. Today we will talk about chapter 1 of this THERMO 2 class, namely Exergy analysis. I know this topic is something new for most of you. So we will look at this topic slowly, step by step, so that you have a better understanding. What does this Exergy mean? This is the learning outcomes of this chapter. First is to demonstrate understanding of key concepts related to exergy analysis, including the exergy referent environment, the dead state, and then exergy transfer and exergy destruction. Second one is to evaluate exergy at a state and exergy change between two states using appropriate property data. So in this case, we will use the same table we have in THERMO 1 and then apply exergy balance to closed system and to control volume at steady state. So if you already forget what do closed system and control volume mean, I suggest you to review THERMO 1. I think it is in chapter 2, and also what does steady state means. So please review THERMO 1. And then the last one is to define and evaluate exergetic efficiencies. This is the content of this chapter. First, we will have a look on the introduction of exergy, and then exergy concept, and then exergy of a system, and then closed system exergy balance, as well as open system exergy balance. And the last topic is the exergetic, or it can be also called second law efficiency. First topic is introducing exergy. In THERMO 1, we already learned about the energy. So we know that energy is conserved in every device or process, but energy can be transferred in terms of heat and work. So here we will show you that the energy conservation idea alone is inadequate for depicting some important aspect of resource utilization. So now let's take a look on this simple system. This system consists of fuel. So you can see in here the fuel. And then this fuel is surrounded by air. And you can also see the boundary of the system represented by a dashed line here. And we call this system as an isolated system. Okay, once again, this isolated system consists of fuel and air. And in THERMO 1, you know that an isolated system means that there is no energy transfer between the corresponding system and the environment. Okay, so once again, in isolated system, there is no transfer of energy across the system boundary. So suppose that, let me go to the next slide. Suppose that the fuel burn, okay, the fuel burn, then there will be a release of energy. In this case, there is a change of the energy form from chemical energy into the thermal energy, so that the environment, which is also inside this isolated system, so it's mean here air. Let me write it down here. So that at the final state, the air surrounding this fuel here becomes slightly warm, okay, and we don't have fuel anymore. So the fuel is completely burned, and then the air surrounding this fuel becomes slightly warm. Why I call this slightly warm? Because we have huge amount of air here compared to the amount of the fuel. Okay, so this is the sequence of the process in summary. So on the left side, the initial state, it is A here. We still have 100% of fuel and then surrounded by air with a temperature of Ti. And then the fuel burn with the time. And then there is an energy transfer from the fuel to the surrounding air, so that at the final condition, the air becomes slightly warm. So in this case, if we apply the energy conservation from A to B and to C, the energy quantity is constant. So assuming if we have, let's say here in A, assuming that is just, let's say 100, okay, and then air here, let's say has energy maybe 10, okay, and then in B, some of the fuel burn, so that let's say the energy inside the fuel here I have 60, so there will be energy transfer from this fuel to the surrounding air, so that the energy within this air becomes 40, which is coming from the fuel, plus the initial energy of air. So it's mean here I have 50. So you can say it's 50 joule or kilojoule, it doesn't matter. And then at the end, I don't have the fuel anymore. So it's mean here the energy is 0. Then all of an energy now is going to air here that's surrounding the fuel and or surrounding the tank here. So that the total energy within this air is 110. Okay. So once again, if you look at on this energy balance itself or energy balance alone, you can see in here from A to B to C, the energy quantity is constant. But from your experience, if I ask you to choose which one do you prefer, I believe most of you or all of you will select the condition in A. Why? Because rather than letting this fuel burn and then spontaneously and transfer the energy to air and then just make the air slightly warm, I would prefer to have this fuel and then burn it inside the engine and then can propel our motorcycle, or I can use this to boil water and then circulate this water into the vapor system and it can propel the turbine. So if I compare with the condition in C, I only have a slight warm air here, and I think I have a limited utilization of this slight warm air. So it's mean from A to B to C, there is a reduction of the potential use for this fuel. So this is the task of this Exergy to represent the level of the fuel, or I can say here in here I can say it's fuel or something else. So the utilization of the corresponding fuel. So this Exergy once again will represent or can be used to quantify the potential use of this fuel. Okay. So once again, from A to B to C, the energy quantity is constant, but the potential use of especially this fuel decreases. This also means that the economic value of the system also decreases. Okay, the next topic is about Exergy concepts. I think most of you are familiar with this feature. So I took this feature from chapter 5 of THERMO 1, this feature illustrates a spontaneous process. So on the first row here, we have a body with a temperature of Ti, which is higher than the temperature of the atmospheric air. So, so it's mean here the system is not at the same state as the state of the atmospheric air. So we know that if we let the system make equilibrium with the atmospheric air, so there will be a spontaneous energy transfer, in this case is a heat transfer from the system to the atmospheric air at the end, and at the final state, at the end here, the temperature of the body will be the same as the temperature of the atmospheric air. And the second system here, I have air inside the tank, and in this case the pressure inside inside the tank is higher than the pressure of the atmospheric air. And then there will be a spontaneous process here where the air will flow out of the tank, and then at the end, at the final state, the pressure inside the tank will be the same as the pressure of the atmospheric air. And then the last one here, I have a mesh hanging with a cable, and then if I rupture this cable, so the mesh here will fall down, and at the final state here, the mesh will be on the floor. So it's mean I will lose the potential use of the potential energy here. So if you look at on this schematic, if the system is a different state from the atmospheric state, there is a potential here to develop a work. So it's mean rather than letting this heat transfer just go to the environment, I can use this this heat to heat up, let's say, water, and then I can flow this water through the turbine. Same thing in here. Rather than letting this air flow out to the atmospheric air, I can put a wheel here. I can put a wheel somewhere here, and then the wheel will rotate, and then I can connect it to the generator, and it will generate electricity, and so on. So another thing is that if once again, if I have a system that is a different state from the environment, so there is a potential for developing a work. And then in here, I can also say work can be developed as the two systems are allowed to come into the equilibrium. So from left to the right here, the system will go into the equilibrium with the environment. So once again, so if I have the body, let's say a temperature of Ti, okay, then rather than letting this heat transfer going to the environment and get nothing, I can flow this heat into the power cycle, okay, and then from the second law of thermodynamics, there should be some of the heat transfer going into the other system which has a lower temperature. This is Q0. And some of this Q can be used to produce work, okay? And this work for sure can be used to lift the mesh, it can be used to rotate a shaft, and then can be coupled with the generator to generate electricity, like this one. Okay, so Exergy here is the maximum theoretical value of such work. Okay, once again, so now you get a little bit idea about what is the Exergy. So in here, we talk about the system consisting of the system inside this body itself, and also the surrounding air here, or I can say this is environment. So once again, Exergy is the maximum theoretical value of such work when the system comes into equilibrium with this atmosphere. Yes. And then we will define later on what is this atmosphere, what is this T0, what is this P0, and so on. Okay, so once again, in the Exergy, we need to have a system, and we need to define the environment. Okay. So in this case, in the previous slide, what you can see there, that environment is the atmosphere. So it is necessary to model the atmosphere used in the foregoing discussion. And this environment is regarded to be a simple compressible system that is large. Why I call this large? It's mean if there is an energy transfer from the system to the environment, there won't be any change of the pressure and temperature of the environment because the size is pretty large. Okay, and then this system will be uniform in temperature and pressure. So in this case, we give a notation of T0 and P0. And so to keep this environment connected with the actual environment, we use a P0 and T0 here as a typical ambient condition. So it is 1 atmosphere and 25 degrees C or 77 degree Fahrenheit. And then the next one is that the intensive properties of the environment do not change significantly. Once again, because we have a large size of the environment here. And also the environment is free of irreversibilities. And you will see when a system of interest is at P0, T0, so it's mean it is in equilibrium condition with the environment. And also, if the system is at rest relative to the environment, we can also say that the system is at the dead state. And at the dead state, it means there can be no interaction between system and environment. Therefore, there is no potential for developing work. Once again, the potential for developing work exists if the system is at different state from the environment. Okay, now let's define the exergy. So exergy is the maximum theoretical work obtainable from an overall system. Why I call this overall system? Because this system consists of the system itself plus the environment that surround the corresponding system. So an overall system here consisting of a system and the environment as the system comes into equilibrium with the environment. Okay, so once again, if we want to get a theoretical world, so this means that the system must be at different state from the state of the environment. And interaction between the system and the environment here may involve auxiliary devices. So this can be a power cycle, and this power cycle can be used to rotate shaft, can be used to lift mass, and then this shaft can be coupled with a generator to generate electricity. Okay, next topic is exergy of a system. Now let's take a look on the derivation of this exergy equation. So the figure on the left side here, we have a closed system with its boundaries. So it is the first dashed line, so the dashed line inside here. And then it is surrounded by environment, and the condition of the environment here is at T0 and P0. And then when this system interact with environment, or when the system comes into equilibrium of the environment, there is a potential work that can be developed, and this is WC. Okay, and you know that exergy is the maximum theoretical work that can be developed when the system comes into the equilibrium with the environment. So from the energy conservation, so the first law of thermodynamics, we have this equation. So delta EC here. So C here is the overall system. Okay. So delta EC here is the change of the energy of the overall system equal to QC minus WC. Okay. QC is 0. Okay, QC is 0 here because we have an overall system boundary here, so outside here, and then we don't have the transfer of heat going outside of this overall system. Okay, and then delta EC, this is the energy change of the overall system, here equal to the energy change of the closed system plus the energy change of the environment. So delta EC, once again, this is the sum of the energy change of the closed system, and the energy change of the closed system here is U0 minus E. Why? Because the final state of this closed system will be the environment state. So in this case, I have U0 and then minus E. E here is the initial energy of the closed system plus, once again, plus delta UE. So this is the internal energy change of the environment. Okay. And then from one of the entropy correlation in chapter 6, we have this correlation between delta U with T delta S and P delta V. Okay, so review it, chapter 6. So in this case, I have the delta UE equal to T0 times delta SE. So delta SE here is the change of the entropy of the environment minus P0 times delta VE. So this is the change of the volume of the environment. Then I have this correlation as well from chapter 6 of the thermo. So delta S equal to entropy destruction. Actually, you have one more term here, which is Q, I think it's integral Q over T. But in this case, it's dropped to 0 because we don't have Q here. Therefore, from this two correlation, this one, I have delta SC equal to, oh sorry, before we combine this one, I have delta SC, so this is the change of the entropy of the overall system equal to the change of the entropy of the closed system plus the change of the entropy of the environment. Okay, so now I can substitute this delta UE here with this correlation. Let me put it in blue, with this correlation, and then I substitute this delta SE here with this correlation. So now I can replace or substitute delta E from this all correlation, and then I can make WC as explicit, so put it on the left side. Then I will have this correlation. Okay, so WC equal to delta U, so this is the internal energy difference between the closed system and the internal energy of the environment, plus P0 times delta V minus T0 times delta S plus KE plus TE minus T0 times sigma, the entropy entropy destruction. So if you remember, the definition of the exergy is the maximum theoretical work that can be developed when the system comes into equilibrium with the environment. So it's mean the maximum theoretical work. So it also mean there is no entropy destruction in the process. So it's mean when we have this sigma equal to 0, then we have a maximum work, and this maximum work is called exergy, and it is formulated here. So this formula actually is this formula when the sigma equal to 0. Okay. The next one is Exergy Aspects. So first, Exergy is a measure of the departure of the state of a system from that of the environment. What does this mean? This means that the farther the departure is, the higher the exergy is. So it's mean the level of difference of the state between the system and the environment is also a measure of the exergy. Okay. Second one is the value of exergy cannot be negative. Okay, so the value of exergy cannot be negative. Why? So if you have a system that is different from the environment and you just let the system goes and then comes into equilibrium with the environment, so it's mean you get nothing. So it's mean exergy is 0. So because you just let it go, you just let the potential here goes and then you get nothing there. So it's mean exergy is 0, but it won't be a negative. Okay. Number 3, exergy is not conserved. Okay, exergy is not conserved, but it is destroyed by irreversibilities. So you will see later on that although the energy is constant, the exergy decreases. Okay, so if you remember from the very first feature in this chapter, where I have an initial system consisting of 100% fuel inside the tank and then surrounded by air, and then at the end I don't have fuel at all, and then the surrounding air is just slightly warm. We can see, or we can calculate later on, that the energy is constant but the exergy decreases. Okay. Okay, the next one. Exergy has been viewed thus far as the maximum theoretical work obtainable from an overall system. So overall system here, so it's mean this is a system plus environment, as the system passes from a given state to the dead state. The dead state here is actually the state of the environment. Okay, the state of the environment is the dead state. So it is at P0, T0, velocity is 0, and the height is also 0. Okay, the last one. When a system is at the dead state, it is in thermal and mechanical equilibrium with the environment, and the value of the exergy is 0. Okay, once again, if the system is at P0, T0, velocity is 0, and the height is also 0, it means the system is at equilibrium with the environment and it is at the dead state, so it also means the exergy is 0. Okay, the next one is the specific exergy. Like in energy, you have specific energy. So it means you also have specific internal energy, you have specific enthalpy. We can also define the same thing for the exergy. So exergy on a unit mass basis. So in here we have a small e letter here. So this is specific exergy. So you divide each term on the right side by the mass. Okay. So if you look at on this formula, it required thermodynamic properties at the state of interest and at the dead state, which is the environment state. If you look at on each parameter here, you need to get what is the specific internal energy at the system state, and then what is the internal energy at the environment state, which is P0 and T0. We also need to know what is the specific volume at the system state and at the dead state, as well as the entropy here. And then the next one here is the information about the kinetic energy and the potential energy. And once again, the kinetic and potential energies are measured relative to the environment. So, and the environment has a 0 height and also at rest. So it means the velocity is 0. Okay, let's take a look on this example. We have a balloon here filled with oxygen, O2, and the state of the system is given here. Temperature is 280 Kelvin, and then pressure 1 bar. And then this balloon has a velocity of 15 meter per second. And then the height relative to the environment, which is Earth here, 0.5 kilometers. Okay, and the T0 is 300 Kelvin, and P0 is 1 bar. And then the question is, using the ideal gas model, okay, ideal gas, I think it is in chapter 3 of THERMO 1. Okay, ideal gas here, if you remember, is P equal to rho R T. Okay, so this is gas constant. So using the ideal gas model, determine the specific exergy of the oxygen in kilojoule per kilogram. It means this is specific exergy, okay? And then takes a G, this is a gravity constant, equal to 9.807 meter per square second. Let's take a look on this solution. Okay, we use this formula to calculate the specific exergy of the balloons. So E here, small e, equal to the internal energy difference between the system and the environment, plus P0 times the delta V, specific volume, minus T0 times delta S, specific entropy, plus the kinetic energy plus the potential energy. So we know the state of the system, so it has temperature of 280 Kelvin, okay, and then the environment has a temperature of 300 Kelvin. So the working fluid is air, so temperature is given. I think you need to use table A23. Okay, so open your table, so go to table A23. This is SI unit, so you go to A23 instead of A23E. Okay, so looking at the internal energy at 300 Kelvin and 280 Kelvin. Okay, so that you can estimate U minus U0. So in table A23, I think the unit of the specific internal energy is in kilomole. So you need to change it to be kilogram basis. So in this case, you need to divide this molar specific internal energy by the molecular weight of air, or of oxygen. Sorry, this is not air, of oxygen. So O2. So the molecular weight of O2 is 32. So check with your table whether this number is correct. So we have U at 280 Kelvin. 280 Kelvin. So U is, I'm also checking with my table here. So oxygen at 280, I have 5822, correct. And then the next one is looking at U0. U0 here is at 300 Kelvin. I think 6242 is correct. Yeah. Okay. So in this case, we got U minus U0 is minus 13.13 kilojoule per kilogram. Why it is minus? Because T is lower than T0. Okay. And then the next one, we calculate P0 times delta V here, and then it is ideal gas. So we can replace V, specific volume, with R times T divided by P. Okay, so this is the ideal case formula. So phi equal to RT over P, and then phi 0 equal to RT0 over P0. Okay, and then sin P equal to P0, so you can simplify the correlation to be this one. Okay, and then you substitute the value there. So you have R here is a gas constant. So R equal to R0. This is the universal gas constant. So 8.314 kilojoule per kilomole Kelvin. And then this divided the molecular weight, this one. Okay. And then time T minus T0. T is 280, T0 is 300 Kelvin. You will get this one. It is also negative because once again T is lower than T0. So we recalculate the first term and second term on the right side. Next one is to calculate the third term on the right side. So this is T0 times S minus S0. So in this case, we use the correlation in chapter 6 of THERMO 1. So delta S here equal to, see here, S with the degree sign that you can get it from the table. Okay. So S minus S0 equal to S degree minus S0 degree minus R time ln. So this is natural logarithmic P over P0. And then because P equal to P0, you can simplify the formula with this one. And you can get S degree and S0 degree from table A23 as well. Okay, so looking at your table again, and I believe S degree is the last column of the corresponding gas. So you go to the oxygen, and then looking at S0 at 280 Kelvin and 300 Kelvin. Okay, you will get this number. And then divided by the molecular weight of oxygen, O2, which is 32. So single O has molecular weight of 16, and then O2 then is 16 times 2. So in this case, you have a positive 18.96. It's positive because here we have a negative sign here. Okay, so we have calculated the first term, second term, and third term on the right side. And then the next one is to calculate the kinetic energy and potential energy. The velocity is given, it is 15 meter per second. And then the height from the environment, which is the Earth, is 0.5 kilometers. You need to convert it to meters. So you will get 500 meters. Okay. We try to make the unit the same as the unit of the first three here, which is in kilojoule. So in this case, you need to divide it by 1000. So the contribution of the kinetic energy and potential energy here is positive 5.02 kilojoule per kilogram. So now you just need to sum up all of the number, and then you will get the exergy of this balloon with oxygen in it is 5.65 kilojoule per kilogram. So I suggest you to repeat again this calculation and then looking at your table and check it if the number is correct. Next example, here we have a cylinder of an internal combustion engine. So it contains 2450 cubic centimeters of a gaseous combustion products. So So this will be the system, and this system has a pressure of 7 bar and a temperature of 867 degrees C just before the exhaust valve opens. Then the question is determine the specific exergy of the gas in kilojoule per kilogram. And then couple of hints here. We can ignore the effects of motion and gravity. So it's mean Ke and Pe are 0. And also model the combustion product as air behaving as an ideal gas. So pretty much similar to the previous example. And then T0 is 300 Kelvin and P0 is 1.03 bar. So I think this is 1 atmosphere. So give a try to solve this one. I suggest you not looking at the solution in the book. Okay, so try it by yourself. So you have a pressure of 7 bar and temperature of 867 degrees C. So you will use the same table as the one we used in the previous example. I believe it is table A23. So looking at the specific internal energy at temperature 867 degrees C. So you need to convert it to Kelvin. So plus 273. If you want to get exact number, plus 273.15. And then you need to do the same thing to get U0 at 300 Kelvin. And then you can replace the entropy change with the correlation in chapter 6. So pretty much similar to the previous example. And if you do it correctly, so you will get this number, that the specific exergy is 368.91 kilojoule per kilogram. Okay. The next subtopic is Exergy Change. So in this case, the system is still a closed system. So it means there is no transfer of mass across the boundary. So a closed system at a given states can attain new states by various means. So one of the easiest way here is by transfer of energy. So can be in terms of work or in terms of the heat transfer. So the closed system can change from one state to the other state. So for example, the system at initial state, it is at 0.1, for example. At this initial state, the system has exergy of E1. So E1 equal to this. So this same as the previous formula. So the exergy at a certain state. So in here we call this initial state. And then the exergy at final state, for example, it is 0.2. Can be formulated the same thing. We just replace the subscript 1 with 2. And then the exergy change from the initial state to the final state is just the difference. So it's means the difference between E2 and E1. So it is formulated as this formula. So it's just straightforward. So E2 minus E1 equal to U2 minus U1 plus P0 time V2 minus V1 and so on. So if you look at this formula, we don't have the parameter or we don't have the specific internal energy, or we don't have the internal energy as well as volume and then entropy at that state. So we don't have U0, no V0, no S0 here, because when we subtract E2, E2 by E1, so these parameters cancel out. So once again, this is the formula to calculate the exergy change when a closed system changes the states from state 1 to state 2. Okay, this one is the schematic to show us how does the exergy change from one state to the other state. On the left side, we have a 3D schematic here. We have 3 axes. So pressure axis here, and then the horizontal one here is the temperature, and then the vertical one here is the value of the exergy. So as you can see in here, we have a point with the black dot here. I believe this is the dead state. So at this point, the exergy is 0. Then when the system depart from this dead state, they have a exergy. So, and then you can see in here ISO line for the exergy, and then if it's going up, so it's when the exergy increases. You can see there. So because once again the system is moving away from the dead state, and then if we make this schematic in 2D, so you will have the picture on the right side. So horizontal line here is the pressure, and then vertical line is the temperature, and the line here is the constant exergy contour. So we have the dead state here where the value is 0, and then once again if the system is moving away from this dead state, it will have higher exergy. So for example, here I have a system at state 1, and then because of maybe energy transfer or something else, the state 1 system at state 1 here change to state 2, and if you can see here, it is moving away from the dead state. So it's mean that the exergy of the system that is doing process A here has a exergy increase. So it's mean the exergy at the final state at point 2 is higher than the exergy at point 1. And then on the contrary, we have a system doing a process here following the path line B. It's changing the state from state 1 here with a single prime to the state 2 with single prime here. If you look at this process direction, it's moving toward the dead state here. So it's mean the system exergy decreases from exergy at point 1 single prime here to exergy at 2 single prime here. Okay, so once again, if the system is moving away from the dead state, the exergy will increase, like showing here with the process line A here. So the exergy at point 2 is higher than the exergy at point 1. Next subtopic is a closed system exergy balance. So the exergy balance for a closed system is developed by combining the closed system energy and entropy balance. So this one has been shown in THERMO 1. So the energy balance, I believe it is in chapter 3, and then the entropy balance is in chapter 6, and chapter 5 is the introduction of chapter 6. So the energy balance for a closed system can be seen in this first equation. So on the left side here represent the chain of the system energy, consisting of the internal energy chain, kinetic energy chain, and potential energy chain. So delta U plus delta KE plus delta PE. And then it is balanced on the right side here by the energy transfer in terms of the heat transfer, and also here by the work. Okay, so this formula follows the convention in THERMO 1, I believe. So if the heat transfer is going to the system, it is positive. If the work is done by the system, it is positive. So, and then the next equation here is the entropy balance. It's from chapter 6, that delta S. So here the chain of the system entropy is balanced by the heat transfer that's happen at the boundary with the temperature T here, and T here is TB plus the entropy destruction. So that's why you know the term isentropic. So isentropic means that delta S equal to 0. It's just to refresh our memory. And isentropic also means adiabatic reversible. So adiabatic means that there is no Q. So Q equal to 0. Internal reversible, it's mean that sigma equal to 0. So it just follow this formula. So if you want to have delta S equal to 0, then it is adiabatic and it is internal reversible. So it's mean each term on the right side is 0. Okay. So we have this formula, and then if we substitute heat transfer in this first equation with the second equation, so you will have this one. So on the left side you have the change of the system energy, and then minus T0 time delta S. Okay, and then on the right side we have first is integral of dq, and then minus T0 integral dq over T0 minus W minus T0 time sigma. Okay, and then the next one, what we can do is we can move this term to the right. Okay, and then so you know the formula of the Exergy Change from the previous slide. You can see it on this top equation, and then by doing a simple equation manipulation you will get this formula. So on the left side it's showing the Exergy Change, and then on the right side we can classify this term into two types. The first type here represent the Exergy transfer, and then the last term here represent the Exergy destruction. Okay, so we will look at individual term here on the next slide. Now let's take a look at the interpretation of the individual term here. So let's take a look on the first term on the right side. So the first term on the right side is interpreted as the Exergy transfer accompanying heat transfer. Okay, so the first term here is this term. So integral from state 1 to state 2, 1 minus T0 over TB time delta Q. So I hope you can recognize this term. Let me use a different color, this term. If you remember in THERMO 1 minus T0 over TB, this is the Carnot efficiency. So if you looking back again, the definition of Exergy, so this is the maximum theoretical energy that can be obtained when the system is moving toward the dead state. Okay, so this one is the Carnot efficiency, and then if we multiply this Carnot efficiency with the Q, it is work, right? It is work. So it's mean, although you see here as the Exergy transfer accompanying heat transfer, this term also represent the maximum theoretical work. Okay, this one is also work. Okay, so TB denotes the temperature on the boundary where heat transfer occurs. So once again, in the Carnot system, you have TB. Here is the temperature of the hot reservoir, and then T0 is the temperature of the cold reservoir. So Looking at again in THERMO 1, it is in chapter 5 and chapter 6 when we talk about this Carnot efficiency. Going to the second term on the right side, the second term on the right side is interpreted as the exergy transfer accompanying work. So I don't need to explain more here because the work is formulated explicitly here. So we have W here, and then the next one, if you get here, so this is P0 times V2 minus V1. So the work that happens, W here, is subtracted by the work required to displace the environment from V1 to V2, okay? And then the third term on the right side, so this one, account for the destruction of exergy due to irreversibilities within the system, okay, within the system only, because the environment is assumed no irreversibility. So no irreversibility inside the environment. So in accord with the interpretation of the entropy production, a term of the entropy balance. So this one. So if you look at on in chapter 6 of THERMO 1, so we also have the entropy production, which is sigma here, and then the exergy destruction here is just sigma times T0, and T0 is the temperature of the dead state or the temperature of the environment. So this one is what we have, and it is in accord with the interpretation of the entropy production. So ED here is the exergy destruction, so it's equal to 0. It means that there is no irreversibilities present within the system, and then it is more than 0. It means no irreversibilities present within the system, and it won't be below 0. So it means it is impossible to have ED below 0. Let's take a look on this example. So water, initially a saturated liquid at 150 degrees C or 423.15 Kelvin, is contained in a piston cylinder assembly. So working fluid here is water. Initially it is saturated liquid. So you can imagine where is the location of this state in the vapor dome. So it is on the left side, exactly at the saturated line. The water is heated to the corresponding saturated vapor state in an internally reversible process at constant temperature. Okay, so if you want to start drawing the process here, let's say I have a TS diagram. So this is temperature. Oh, sorry, this one is entropy, and then this is temperature. So this is the dome, and then we have a constant pressure here, P equal to constant, and then saturated liquid, it will be here. So this is state number 1, and then state number 2, it's going to saturated vapor at constant temperature, this process. So it's horizontal line here. Okay, so for T0 equal to 20 degrees C or 293.15 Kelvin, and P0 is 1 bar, and ignoring the effect of motion and gravity, so it's mean Ke and Pe R0 determined per unit of mass. So it is in specific unit, each in kilojoule per kilogram. A is the change in exergy, and then B is the exergy transfer accompanying the heat transfer, and C is the exergy transfer accompanying work, and D is the exergy destruction. So it is ED equal to 0 times sigma. Okay, let's take a look on the solution of this example. Okay, on the left side is showing the schematic of the system. So the working fluid is water. So assuming here we heat this water so that it's changing the state from state number 1 to state number 2. So you can see this process line in the PV and TS diagram. So from state 1 to state 2, the temperature as well as pressure are constant. And then on the right side, here is the engineering model or assumption. First is the water in the piston cylinder assembly is a closed system, so it means there is no transfer of mass. And then a second assumption here, the process is internally reversible. And then number 3, temperature and pressure are constant during the process. It's clear here. And then number 4, we need to ignore the effect of motion and gravity. And number 5, this is the dead state condition. So 293.15 Kelvin and 1 bar. Okay, this example is actually from example 6.1. So it is in chapter 6. So you can make a quick review on this example 6.1. And then from this example 6.1, we already got what is the specific volume, specific internal energy, and specific entropy at state 1 and state 2. You can check with your table, so it should be straightforward. Temperature is given, so I believe it is table, let me check, I think it's table A2, I believe. Let me check, quick check here. It is table A2, yeah, table A2, and then go with the temperature of 150 degrees C. Okay, so you should be able to get the number in this table. And then from example 6.1, we got already what is the work, so W per M, so the specific work, as well as the heat transfer per unit mass of the water here. So it's 2114.1 kilojoule per kilogram. Okay, so we already have the properties data as well as W and Q, and then we can estimate other parameters, so like the change of the exergy and so on. Okay, first is the question is what is the exergy change per unit of mass. So we have this formula. So we need to find out what is U2, what is U1. We already have it in the, you can check again on the previous slide. And then P0 is given, and then V2, V1, specific volume. We have this one, T0 is given, and then S2, S1 was also obtained from example 6.1. So you just need to plug in this number, okay? Make sure that you use the correct unit, make a conversion if needed, okay? So for example, pressure is 1 bar. You need to change it to a Pascal, and Pascal here is Newton per square meter here. So multiplied by 10 to the power of 5 from 1 bar to Pascal unit. So you just plug in all the number, you will get this value. So the change of exergy from state 1 to state 2, it is 502.38 kilojoule per kilogram. Okay, give a try. So once again, when you take this thermodynamic and then also following this class, it is not sufficient just by following this class and then hearing my presentation here. No, you need to give a try by yourself. Use a scratch paper, use your pencil or your pen, and then try to solve it yourself, looking at the table, and so on and so on. Next one, the question in B is, I think, is the exergy transfer accompanying the heat transfer. So we also have the formula. So this one. So 1 minus T0 over T times Q over M. So all parameters are given here. We have a T0, we have T, Q has been shown in the previous slide from the result of example 6.1. And then you just plug in all the number and you will get this one. So the exergy transfer accompanying the heat transfer is 649.49 kilojoule per kilogram. And then the next one is the exergy transfer following the work. So here we have this formula. So it is W over M minus P0 time V2 minus V1. So we also have all number here. You just plug in and you will have the number here, 147.21. So looking at this formula, so you can see in here that the exergy transfer accompanying the work is slower than the work itself, the W. So if you're looking at the PV diagram, the amount of a W is the area surrounded by point 1. So look at the PV diagram on the top right feature here. So W is represented by the area surrounded by point 1, point 2, so 1, 2, and then D and A, okay? And then this term P0 times V2 minus V1, this is the area represented by this one. It is surrounded by point B, C, D, and A. So the exergy transfer accompanying the work is W minus P0 times V2 minus V1. It is this area. Okay. And this P0 times V2 minus V1 is the work that is required to displace the environment from V1 to V2, okay, from V1 to V2. So there is less work here represented by the exergy transfer accompanying the work. Okay. The next question is the exergy destruction, I believe. Yep. So if you look at back in the previous slide, there is one assumption that the process is internal reversible. So it's mean sigma, let me use different color. It's mean that sigma equal to 0. So it's mean AD, the exergy destruction, is also 0. Okay, but you can prove this number by plugging all the number that you have from A, B, C, and you can check it, and the value will be 0 because you already have the exergy change from A, and then you have the exergy transfer accompanying the heat transfer, B, and you also have the exergy transfer accompanying the work. And then if you plug in all this number, and then you make ED over M here is explicit on the left side, you plug in all the number here, you will get also 0 here. Okay, but once again, in the actual exam, if you don't have sufficient time, you know the process is internal reversible, you might not need to use this one. You just answer this one, that because it is internal reversible, sigma equal to 0, and then because ED equal to sigma times T0, then ED is also 0. Next one is exergy rates balance of a closed system. So on a time rate basis, the closed system exergy rates can be formulated by equation 7.10. So here we just divide each term in the exergy rate in the exergy balance by dt. So you will have equation 7.10, and then see if the system at a steady state, then equation 7.10 reaches to give this formula. So equation 7.11a. So once again, if it is this steady state, it's mean all parameter doesn't change with the time. So it's mean this one 0, okay, and then dv over dt is also 0. Then this equation will simplify and we will get equation 7.11a here. So in this case, you can see that the exergy transfer accompanying the work at the steady state is just the work, okay? Because there is no P0 dV over dt. Okay, so so again here equation 7.10, and then we have equation 7.11a on the right side. So in both expression, the term E with the subscript Qj, so this is the exergy transfer accompanying the heat transfer. So this one is represent the time rate of exergy transfer. And then at rate Qj, so this is the heat transfer rate, and then the temperature of the boundary where the heat transfer occurs is Tj. Okay. Also in here you can see the Ed. So this is with the single point on top of the E. So this is account for the time rate of exergy destruction due to irreversibilities within the system. So the same thing as the formula without the rate, but in this case everything is normalized by the time. Okay, and finally note that for a system at steady state, so steady states, it means no parameter change with the time, the rate of exergy transfer accompanying the work, but in this case because it is rate, so work per time is the power. So in this case the rate of exergy transfer accompanying the power, so W with the point on top of W is simply the power, because P0 dV over dt is 0 here, so at steady state. Okay, let's take a look on this example that represent the exergy rate balance for a closed system. So we have a cylindrical rod insulated on its lateral surface, and then it is in contact at one end with a wall at T1 600. So it is on the left side here. So this is the wall, and the temperature is 600 Kelvin. And the other end at T2, so here other end, T2 is 310 Kelvin, is exposed to the atmosphere, which is at T0 equal to 300 Kelvin. So this one is also T0 here. At steady state, energy is conducted by heat transfer through the rod at a rate of 100 kilowatt. So there is a heat transfer through the rod, and the amount is 100 kilowatt. The question is A, the rate of exergy transfer accompanying heat transfer into and out of the rod, and then B is the rate of exergy destruction within the rod, and C is an accounting of the exergy entering the rod. So let's take a look on the solution of this example. So the rate of exergy transfer accompanying heat transfer into and out of the rod can be estimated by this formula. So on the left side, so it's the exergy transfer going into the rod. So T0, we have it, and at T1, it is also given 600 Kelvin. And Q is also given there. So here we have 50 kilowatts. So from the left side, we have the exergy transfer with the amount of 50 kilowatt. And then on the right side, the exergy that is out of the rod. So here we have this formula. So we replace T1 by T2. So the exergy transfer leaving the rod is 3 kilowatt. You can see there, exergy is not conserved. So entering the rod, we have 50 kilowatt exergy, but leaving the rod, we have only 3 kilowatt. And then the next one, we can apply the exergy rate balance from equation 7.11a. So here we have a 0 because this is a steady state equal to exergy transfer accompanying the heat transfer from the left. This is exergy transfer accompanying heat transfer leaving the rod. So it is on the right side. And we have work, and then we have exergy destruction here. So work, it is 0. There is no work on this example, okay? So it's mean, so we have EQ1, we have EQ2, and W is 0, then we can easily get ED, okay? So ED is just EQ1 minus EQ2. So you can see in here, so ED, which the exergy destruction, it is 47. So once again, entering the rod, we have 50 kilowatt. It's pretty high exergy. But when it's leaving the rod, it's only 3 kilowatt. So we lost 47 exergy here. Okay. So the irreversibilities in this case, so with this 47 kilowatt, is the spontaneous heat transfer within the rod from high temperature end to the lower temperature end. So you can see while the rates of heat transfer are the same at each end of the rod, so because the rod is isolated laterally, so it means the heat transfer from the left is 100 kilowatt, and then leaving the rod on the right side is also 100 kilowatt. But you can see that the rate of exergy transfer at the ends are much different, right? On the left side, we have 50 kilowatt. On the right side, we only have 3 kilowatts. So 47 exergy are lost inside the rod. So the exergy transfer rate here provides truer measures of thermodynamic value than the heat transfer rate. So the thermodynamic value of the heat transfer depends on the temperature at which it occurs. And the magnitude of exergy transfer rate at high temperature hence signals an opportunity for doing something useful. Therefore, on the left side, because the end temperature is higher, you have higher exergy transfer. And then on the right side, the end temperature is low, it has also lower exergy transfer. So the smaller exergy transfer rate at the low temperature ends indicates much reduced usefulness, but still there's an opportunity there because we still have 3 kilowatt. So you can do this 3 kilowatt maybe for heating water or something else. But if you let it go, then it will be just an exergy loss. So this is the exergy accounting for the rods. So we have a rate of exergy in from the left, it is 50 kilowatt. And then the rate of exergy out is only 3 kilowatt, so it's 6%. And then the rate of exergy destruction, it is 47 kilowatt, which is 94% of the rate of exergy in. So in principle, the exergy transfer from the rod can be used for some purposes. So accordingly, it is accounted for here as an exergy transfer out of the rod. So however, as this exergy is not used in the surrounding, as I mentioned previously, it is more appropriately charged as an exergy loss for the rod. So although you still have 3 kilowatt there, but if you let it go, if you don't use it for something else, this will be also an exergy loss. So 50 kilowatt will be completely lost to the environment. And the next one here is the exergy transfer from the rod is fully destroyed in the surrounding owing the heat transfer irreversibilities there. So this is within the rod. In the end, all of the exergy entering the rod is destroyed. So as I mentioned to you, if you don't utilize this 3 kilowatt exergy, then it will be an exergy loss. So it's mean all 50 kilowatt here will be destroyed. It will go to the environment. So it's mean missing a seeming opportunity in this case. Let's take a look on this second example. So here we evaluate exergy destruction in an oven wall. So here we have a wall of an industrial drying oven. This wall is constructed by sandwiching 0.066 meter thick insulation having a thermal conductivity of K here 0.05 times 10 to the power of minus 3 kilowatt per meter Kelvin between thin metal sheet. So you have insulation, and then on both sides it has a thin metal sheets. That's why it's a kind of sandwich here. At the steady state, the inner metal sheet is at temperature T1 575 Kelvin, and the outer sheet temperature T2 is 310 Kelvin. And then it is also assumed that the temperature varies linearly through the wall. The temperature of the surrounding away from the oven is 293 Kelvin. Question here: determine in kilowatt per square meter of the wall surface A, the rate of heat transfer through the wall, and then B is the rate of exergy transfer accompanying heat transfer at the inner and outer wall surface. Okay, and then C is the rate of exergy destruction. Also here we can define T0 here equal to 293 Kelvin. Let's take a look on the solution of this example. So on the right side here is the schematic of the system. So once again, the wall is a kind of a sandwich wall. So we have insulation layer here with the thickness of 0.066 meter, and then on the left side we have a thin metal temperature of T1 here at 575 Kelvin, and then on the right side we have also a thin metal. The temperature is 310 Kelvin, and it is assumed that the temperature varies linearly within this wall. So you can see this linear line here. Okay, and then okay, so I let you to try solve this example. Once again, my suggestion is don't look at the book. Okay, I know there is a solution in the book, but try to solve it yourself, and then just follow the same method like what we have in the previous slide, and then solve it. And then if you get stuck, then you can start looking at the solution. But once again, my suggestion, try to solve this first, and if you solve it correctly, you will have the solution shown in this slide. So for example, like A, you will get the heat transfer in the amount of 0.2 kilowatt per square meter, and then B, you will get 0.1, and then B, the second question, you will get 0.01. So, and then C here is the exergy destruction, where you get 0.09. So you can see from the solution that the exergy entering the wall is 0.1, and that the exergy leaving the wall is only 0.01, and then the exergy destruction is 0.09. So it means 90% of this exergy is destroyed within the wall. Okay, and also if you don't utilize this exergy leaving the wall, it will be also an exergy loss. So it's mean this 0.1 exergy transfer entering the wall will gone completely without any utilization of it. Okay, the next subtopic is exergy rates balance for control volume at steady state. Okay, control volume, so it's mean volume is constant, but the mass can flow across the boundary of the system. Okay, let's take a look on how this exergy balance is developed from this control volume system. The exergy rate balance for a control volume can be derived using an approach like that employ in the mass flow derivation in chapter 4. Okay, so I suggest you to have a quick look in chapter 4 on how the mass flow equation was derived. So here on the left side we have the Exergy change of the system. Here is a function of here it is normalized by the time because this is in terms of the rate. And then on the right side, first term, it is the Exergy transfer accompanying the heat transfer. And then we have the Exergy transfer here accompanying the work. And this one is the new parameter. So this is the Exergy flow following the mass, okay? Because it is a control volume, so the mass can flow across the boundary. And similarly, we also have the exergy flow that accompanying the mass, okay? And then the last term here represent the exergy destruction. And then at steady state, so it's mean no parameter change with the time. So it's mean this one is 0, and then this one is also 0. Then this equation can be simplified to equation 7.13a. So on scan, EFI account for the exergy per unit mass entering at inlet I, and then you also have EFE. So this account for the exergy per unit of mass leaving at exit E. Okay, so this is the way the exergy balance is developed. So exergy per unit mass can be derived from the energy and entropy balance of control volume. So this is schematic of control volume. On the left side, we have state number 1 here. We have H, S, V, and Z. And then this control volume, so we have a Q entering the system, we have also W leaving the system, and then on the right side, so we have the condition at the dead state, okay, at the dead state. So if we apply an energy balance, so we have this formula, okay, we have this formula. So this is at steady state, so it's mean on the left side it is 0, we have Q, we have W, and positive negative here once again is following the convention in chapter 3. So Q is positive if it is entering the system. Okay, so and then plus M time H minus H0 plus 3 plus blah blah. So this is the energy flow entering the system minus the one leaving the system. And then the next question here is the entropy balance of the open system in chapter 6. Okay, so on the left side, so it is 0, and then once again because it's steady state, and then you have Q, you have the entropy flow here, and then you have a sigma here. And then if you make a W as an explicit, okay, you make W as an explicit, and then you replace QCV on the first equation by the second equation, then you will get this one. So this is W CV over M. This is equal to this equation minus this one. Okay, so exergy per unit mass can be derived again from the energy and entropy balance, and you will get this one. So with this actually same as the formula in the previous slide. Okay, so this one is showing us a schematic comparison between energy and exergy for control volume. So as I mentioned to you at the beginning of this presentation, that energy is conserved, because this is the rule from the first law of thermodynamics, but exergy is destroyed by irreversibilities. Okay, so looking at this schematic on the left side, we have an energy analysis for control volume. On the right side, we have exergy analysis for control volume. So on the energy analysis, you can see there that we have an energy entering the inlet I here, 10 megawatt, and then there is a heat transfer entering the system. It is 90 megawatt. So it's mean here we have 100 megawatt energy into the system. And then on the other side, the system is doing work. It is of 40 megawatt. And then the energy leaving the system following the flow, it is 60 megawatt. So you can see in here, energy in is 100 megawatt. Energy out is also 100 megawatt. So it's mean energy is conserved here. And now it's moving to on the right side. This is the exergy analysis. So the exergy entering the system here, it is 2 megawatt. So if you want to do calculation, you can do it yourself. So I think in the book it is shown the state and so on. You can calculate the exergy flow using the previous equation. So you will have 2 megawatt, and then Q, this one is the exergy transfer accompanying the heat transfer. So this is 1 minus T 0 over T of the boundary. So you can check the book what is the temperature of the boundary, and you get 60 megawatt. Okay, and then the exergy transfer accompanying the work, it is a steady state. It is also the work W, therefore it is also 40 kilowatt. So we have 40 kilowatt. This one we also have 40 kilowatt here. Okay, and then the exergy leaving the system following the flow here at exit E, it is 15 megawatt. Okay, now let's take a look on this exergy accounting. Exergy in, it is 60 megawatt. This is accompanying the heat transfer, plus 2 megawatt. This is of accompanying the inflow. So we have 62 megawatt exergy in. And then exergy out, we have 40 megawatt. This is accompanying the work. And we have 15 megawatt. This is following the flow out of the system. So we only have 55 megawatt. So you can see in here, and there is a difference of 7 megawatt here between exergy in and exergy out. And this is the exergy destruction within the system. So you can see now the difference. The energy is conserved. So in, out are the same. But exergy is destroyed by the irreversibilities. So in is 62 megawatt, out is only 55 megawatt. So 7 megawatt is destroyed by irreversibilities. Let's take a look on this example. So we need to determine the exergy destruction in a throttle valve. So it is also an interesting example because in throttle valve, if you know in THERMO 1, so enthalpy is constant, okay, but you will see that there is irreversibilities within the throttle, so the exergy out is less than the exergy in. Okay, so superheated water vapor enter a valve at 500 pound-force per square inch. So this is a British unit. 500 degree Fahrenheit, and exit at a pressure of 80 pound-force per square inch. The expansion is a throttling process. Once again, throttling process is mean enthalpy out equal to enthalpy in. Question: determine the exergy destruction per unit of mass flowing in BTU per pound. And then T0 is given here, 77 degree Fahrenheit, and P0 is 1 atmosphere. Let's take a look on the example. Let's take a look on the solution of this example. Okay, so knowing here is the water vapor expand in a throttling process through a valve from a specific inlet state to a specific exit pressure. And the question is determine the exergy destruction per unit of mass flowing. And this one is the schematic, so it's flow from left and the right. So at the end range, it is given that the pressure is 500 pound-force per square inch. So this is PSI actually, and then temperature is 500 degree Fahrenheit. And then leaving the valve, the pressure, it is only 80 PSI. And then on the other side here is showing the assumption. So first is the control volume is showing in the accompanying figure is at steady state. So it is steady state. And then for the throttle valve of process, so Q equal to 0, W equal to 0, and then T0 and P0 is given here. So before I forget to mention to you, so when you solve a problem in the exam or homework, I strongly encourage you to use this step. Okay, so what is known, and then what we need to find, and the next one is the schematic, and then assumption, and then the analysis. Okay, so that's mean if you do this step by step, and then you don't have the solution, or it's mean your solution is wrong or you don't know how to solve it. But if you write it down up to this one, I will give you appreciation, and the point can be up to 15%. Okay, so keep in mind for this one. Okay, and then okay, now let's go ahead here looking at the analysis. This is a throttle process, as I mentioned to you, that the enthalpy in equal to the enthalpy out, so it's mean H2 equal to H1. So this means that at the exit, so we have the pressure and we can get the enthalpy from state 1. Okay, so state 1 we have two given properties here, pressure and temperature, and then by using the appropriate table you can get what is H1, and then you can also get other parameter like S1 and so on. Okay, so it is a steam at 500 psi and 500 degree Fahrenheit. You can use first you need to check. Oh yeah, in the problem it is given already water vapor, so it's mean it is vapor on the right side of the vapor dome. So in this case you need to use table A4, and because it is British unit you need to use table A4E. Okay, go to table A4E. Looking at pressure 500 psi and temperature of 500 Kelvin. Okay, then you will get enthalpy this number and then entropy this number. Okay, but it is saying here that you need to do an I don't think you need to do interpolation. Let me check my table here. So 500. My table. Okay, let me I need to find out where is the table here. Okay, so table A4. So 500 and 500. Okay, we have the number here. You don't need to do interpolation. Okay, 500 psi and 500 degree Fahrenheit. The number is there, so you don't need to do interpolation. Okay, for example, you will have H1 here is 1231.5, 1231.5. Yes, here. Okay, and then to get the properties at state 2 at the exit, so you have P2 80 psi and H2 equal to H1, and in this case I think you need to do interpolation, okay, to get the entropy and so on. Okay, next one with the assumption listed, so steady state and so on. So the Exergy rate balance, so it is equation 7.17. You will have, or you can get the simple or simplified equation as shown in this slide. So there is no heat transfer, there is no work. Okay, and then you can calculate this one, the exergy flow, and then finally you can get the exergy destruction. Okay, so the exergy destruction here can be calculated with this equation B. So you just need to calculate what is the exergy flow in minus the exergy flow out. Okay, so and the formula is given in the previous slide, so you can use this formula. So there is no change of the enthalpy, therefore this is 0, and then we can ignore the effect of kinetic energy and potential energy, so that you only have this term. Okay, so you can calculate the exergy destruction as the T0 time delta S. So you have this one, 100.8 BTU per pound. You can see in here that the enthalpy is constant between in and out, but we did see the exergy destruction here. Okay. The last topic of this chapter is exergetic efficiency, or sometimes it is also called second law efficiency. The objective of this section is to show the use of the exergy concept in assessing the effectiveness of energy resource utilization. So we will use this parameter to quantify how effective the utilization of the energy resource. There are a lot of tasks that involve the combustion of coal, oil, natural gas, or other energy resource. And these tasks include, for example, like space heating, and then heating in industrial furnaces, and then a steam generator for the steam power plant, or hot gas generator for a gas power system. So when the product of combustion are at a temperature significantly greater than required by a given task, the end use is not well matched to the source, and the result is inefficient use of the fuel burn. So this feature showing a schematic of a closed system on the left side. So for example, we have a fuel burn here, and then it produces the heat transferring to the system at the temperature Ts. So Ts here is a temperature where the heat transfer occurs, Qs, going into the closed system. And then on the right side, we have a Qu. So this is the heat transfer or the energy that it's used for a certain application. It can be used for space heating or industrial furnaces, or for generating steam for the power plant. And then we also have a losses here through the wall. It is Q1, and this heat transfer loss occurs at the temperature T1. And then the Qu here occurs at the temperature Tu. And then we can apply an energy balance here on this closed system, assuming this is steady state. So we have this energy balance. So dE over dt, this is 0. Once again, this is steady state, no parameter change with the time. It is balanced by Qs minus Qu. So positive Q means it's going into the system. And then minus Qu minus Q1, and then minus W. So this is the work, but in this case we don't have W, so it is 0. And then similarly, we can also apply the exergy rate balance, and this is a closed system at steady state, so this one is also 0. And then we have 3 exergy transfer accompanying the heat transfer, Qs, Qu, and Q1. No work here, so this is 0. And then this one is also 0 because it is steady state, so dV over dt equals to 0. And then we have also exergy destruction here. So the first equation can be simplified into equation 7.19a, and then the second question can be simplified into equation 7.19b. So here we have 2 equations. One is the energy balance, second one is the exergy rate balance. So with this two equation, we can do further calculation estimating the efficiency based on the energy and also the exergy efficiency, or we call this one second law efficiency. So now let's take a look on this one. So based on the energy, so we know that the efficiency is what we gain. In this case is QU, and over what we pay. So in this case, we need to pay the fuel. So using the energy based data, we have efficiency formula of 7.20. So in this case, eta, so this is the efficiency based on energy, equal to QU over QS. Okay. So once again, this is the ratio of what we gain over what we pay. Okay, this one. And then similarly, we can also use the exergy information to estimate the efficiency based on the exergy. So once again, the ratio here is what we gain, so what's or which exergy that we can utilize over what exergy that we need to pay. So in this case, the exergy transfer that accompanying QU is what we gain, and then the exergy transfer that accompanying QS is what we pay. Therefore, we have equation 7.21a. So epsilon here, this is the exergetic efficiency, or it is also called second law efficiency. So if you're looking at equation 7.20, so where you have eta equal to QU over QS, so you can substitute this term by eta. Then you will get equation 7.21b. So in this case, we have a correlation that connect the eta, so efficiency based on the energy, to the epsilon. It is efficiency based on the exergy. So now you can see on this equation 7.21b, if you want to have eta equal to epsilon, then what you need to do there is you need to make Tu equals to Ts. So in this case, once again, if your eta is, let's say, 100%, although it is not possible, yeah, you always have efficiency below 100%. So assuming your eta is 100%, if you want to have epsilon equal to 100% as well, you need to make Tu equal to Ts. So in this case, you need to match the temperature where you utilize the exergy to the temperature where we get this energy, which is Ts. So to maximize the utilization of the energy resource, we need to match Tu with Ts, so that the exergetic efficiency, or the second law efficiency, equals to the efficiency based on energy, which is eta in this case. This graphic will help us to understand better the correlation between epsilon and then Tu and then eta. So the vertical axis here represent the epsilon. So this is the exergetic efficiency. And then in this case, we assume that the efficiency based on the energy is 100%, or it is 1. Yeah, so the efficiency is 100% or 1 here. And then we have Tu that's vary here from left to the right. So it is on the horizontal axis here. This is Tu. And then Ts is 2200 Kelvin. So this is temperature close to the combustion. So combustion temperature, it is usually like 2500 Kelvin or 2600 Kelvin. But if you put more oxygen or you put more EGR, exhaust gas recirculation, so you can learn this one in more detail in the internal combustion engine subject. So if you have more oxygen or you have more exhaust gas recirculation, the temperature can be lower to 2200 Kelvin. Okay, back again to this chart. So we have TS 2200. So now if you have a TU, which is, let's say, 300, so your TU is 300, so much lower than TS. So your epsilon will be somewhere here. So it is much lower, right? So you have 0.4, 0.3, 0.2, 0.1. So it's close to 0 here. Okay, it's close to 0 because your TU is close to T0. So if your TU close to T0, then you have epsilon that's close to 0 as well. So now if we increase TU, let's say we're looking at the application of the space heating. So it's cold here. So the space heating temperature maybe couple or a tenth degree higher than 300. So you have at this point. Now you have epsilon value of around 0.10 or 10%. And then if you increase TU, so here we're looking at different application, for example, like process steam generation. So usually it is around 500 Kelvin. Now your epsilon, your exergetic efficiency is close to 50%. And then heating in industrial furnaces, usually it's operate at a higher temperature. So let's say here it is about maybe 700 Kelvin. Then your exergetic efficiency will be around 70%. So from this figure, you can see as we increase TU, especially as TU approach TS, then epsilon will also goes to be close to the eta value, which is 1 here or 100. And so this eta line, so with this one here is a kind of the asymptotic line, and this epsilon line will approach this line as we increase TU. Okay. Okay, now let's take a look on the exergetic efficiencies of common components. So in Thermo 1, I believe we introduced you several mechanical or thermodynamic components like turbine, compressor, pump, and then simple heat exchanger and so on. So now let's take a look on the application of this exergetic efficiency to the common component. First is looking at the turbine. So in the turbine, so turbine is a control volume. So this is an open system. So from the exergy rate balance of the open system, in this case is turbine, we have this equation. So on the left side, we have 0 because it's steady state. And then in this case, we assume that the turbine operates under adiabatic condition. So there is no heat transfer from the turbine to the environment. So Q is 0. And then for sure, turbine will generate power. And then because turbine is an open system, there will be a mass flow in and out through or over the boundary of the turbine system. So in here we have exergy flow in and out. And then the last term here is the exergy destruction. So we can simplify this equation to get equation 7.23. On the left side, we have the exergy decrease. So in this case, the exergy flow decrease that is used to generate the power. So here, plus the exergy destruction. So in this case, we can define the exergetic efficiency from the turbine. Here is the ratio of what we gain, so what exergy we gain, so in this case is the power, over what exergy that we pay. So in this case we pay the exergy flow difference between the inlet and outlet, because at the inlet, so we have a very high exergy or very high energy. It's just out of the steam generator, so we pay money or we spend money to generate the vapor inside the steam generator there. So equation 7.24 here is the exergetic or second law efficiency from the turbine. So it is the power over the exergy flow difference between in and out. Okay. The next one is from the compressor or pump. So for the compressor, for the pump, it means we need to put the energy in there, and what we gain is the increase of the energy or the increase of the exergy at the exit of this compressor and pump. So if we apply the exergy rate balance to this open system, then we have this equation. So this one after we simplified it from this equation. So we don't have a heat transfer, so it's mean we assume that the process is adiabatic and it is steady state. So the exergetic efficiency or the second law efficiency of the compressor and pump is formulated by equation 7.25. This is the ratio of the exergy flow increase. So this is EF2 minus EF1. So because the exergy at the compressor or pump exit is higher than the exergy at the inlet side, over what we pay. So in this case, it is the work. So we put the negative here because the work is coming into the system. So it is negative, negative, so it's become positive. So with this equation 7.25, we can estimate the exergetic efficiency of the compressor or pump. Okay, next one is the heat exchanger. First, we looking at the heat exchanger without mixing. So we have two streams here. On the upper side, we have the hot stream. So entering at point 1, exiting at point 2. So it doesn't mix at all with the cold stream on the bottom side. So the cold stream enter the heat exchanger at point 3 and exiting at point 4. So in this case, there will be a heat transfer from the hot stream to the cold stream. Yeah, so this is the heat transfer. But there is no heat transfer from this heat exchanger to the environment. This one 0. Okay, but this one is not 0, because there is an energy transfer in terms of the heat from the hot stream to the cold stream. Okay, if we apply exergy rate balance to this open system, then we have this equation. So once again, there is no heat transfer between the heat exchanger and the environment. So this one is 0. This one is 0. Okay, and then there is no work. Okay, there is no work at all here. This one is also 0. And then we have exergy flow. First here is the exergy flow entering the heat exchanger. So in here is through point 1 and through point 3. So here it's entering the system. So it's positive, minus the exergy flow leaving the system. In this case is through point 2 and point 4, this one, minus the exergy destruction. So for this heat exchanger without mixing, the exergetic efficiency is what we gain. So in this case is the energy received by the cold flow, this Q, the Q, but this one is, because this is exergy, so we need to multiply this Q by 1 minus T over Ts. And so on. So back again to the exergetic efficiency formula, equation 7.27, the exergetic efficiency from this heat exchanger without mixing is the increase of the exergy flow in the cold stream over the reduction of the exergy flow in the hot stream. Okay, but in this case we want to make every number positive, so you can see in here that on the numerator we have the exergy flow in 0.4 minus the one in 0.3, it is positive, over the mass flow time the exergy flow entering the system 0.1 minus the exergy flow leaving the system 0.2 in the hot stream side. The next one is the heat exchanger with a direct contact. So in this case we had the hot stream entering the system at 0.1, and then we have the cold stream entering the system at 0.2, and both streams mix and exiting at 0.3 here. Okay, and then this is the exergy rate balance for this system. So there is no heat transfer between this heat exchanger and the environment. So this one is 0, and then there is no work, and then we have the exergy entering the system through inlet 1 and inlet 2, and then the exergy flow leaving the system is through the outlet 3, and we also have the exergy destruction here. And then we know that the m.3 equal to m.1 plus m.2, so this is the mass balance. And then we can simplify this first equation to get equation 7.28, okay, by using this formula for the mass balance. And the exergetic efficiency for this direct contact heat exchanger is formulated by equation 7.29. Same thing, what we gain over what we pay. So what we gain here is the increase of the exergy from the cold stream. And here is m.2 times the specific exergy flow at the exit, so this is 0.3, minus the exergy entering the system at 0.2, over what we pay. What we pay here is the exergy entering the system through the 0.1, and this is the mass flow is m.1 times the exergy flow entering this system at 0.1 minus the exergy, so specific exergy leaving the system at 0.3. Okay. Let's take a look on this example. So we will use example 6.11 to estimate the exergetic efficiency of a turbine. So in this example, the inlet condition is given. So P1 is 5 bar, and then T1 is 320 degrees C, and then the exit condition is given in terms of the pressure, it is 1 bar. And then the turbine efficiency based on the energy is 75%. Okay, so once again we will estimate the exergetic efficiency of this turbine, and we can use T0 as the reference. Here is 298 Kelvin. Okay, so in THERMO 1, I believe I already showed this one to you, how this example was solved. So once again, for the solution, try to follow this step, what is known. So in this case, we have a steam expand through a turbine, and then operating condition at the inlet is given, and then the pressure at the exit is also given. And this is the schematic of the HS diagram. So the inlet condition at 0.1 here, pressure and temperature is given, 5 bar. And then at the exit, the condition is also given in terms of the pressure. Okay, in terms of the isentropic process, so the entropy stay the same. So we have 2s point here, but in reality, because there is entropy destruction and so on, entropy production or exergy destruction. Yeah, so we have a 0.2 here on the right side. So the entropy increases because of irreversibilities, and this is the assumption we use in example 6.11. So it is a control volume, and then there is no heat transfer between the turbine and the environment. Therefore, the process is adiabatic here. and we can ignore the change of kinetic and potential energy. I think you already see the solution in THERMO 1. So at state 1, at the inlet, pressure is given, temperature is given. So pressure is 5 bar, I think, and temperature is 320 degrees C. So you can use table A4 because we know that state 1 is a superheated condition. So go to table A4, 5 bar and then 320 degrees C. You will get the enthalpy at state 1. So it is 3105.6 kilojoule per kilogram. And then S1, the specific entropy at the inlet, it is 7.5308 kilojoule per kilogram Kelvin. And then for the isentropic process, S2S equal to S1. And then you can use table A4. So the pressure is 1 bar, and then H2S can be obtained based on the information of the pressure and the entropy. So once again, S2S equal to S1, then you will get H2S. And then from the information of the efficiency and then H1, H2S, we got this work of the turbine. So now we will extend this problem to estimate the exergetic efficiency. So using equation 7.24, I showed the equation on the top right side here. So this exergetic efficiency is the ratio of the work over the change of the exergy flow. And the exergy flow at the individual point can be calculated using this one. We only need to calculate the exergy flow difference between point 1 and point 2. So we have EF1 minus EF2. So H0 will cancel out, and then we can also assume that this one is also 0. So in this case, I will have H1 minus H2, okay, minus T0 times S1 minus S2, okay. So H1 is given already, or has been calculated already, and then H2 we need to calculate it, and then T0 is given. T0 is 298 Kelvin, and then S1 is also here, and we need to calculate S2. Okay, so first let's calculate H2. Okay, so H2 can be calculated from the efficiency formula based on the energy. Okay, so in this case we have efficiency of the turbine equal to H1, okay, minus H2, okay, over H1 minus H2S. Okay, the turbine efficiency is known. H1 has been calculated, and then H2S have been obtained from the table. So we can get H2. So here H2 equal to H1 minus, okay, H1 minus turbine efficiency times H1 minus H2S. So we plug in all the number here because H1 is known already here, 3105.6 kilojoule per kilogram minus the efficiency is 75%, 0.75 times H1 is 3105.6 minus H2S, it is 2743. Okay, so use your calculator to estimate or to calculate H2, and I think let me use my calculator to calculate this one. Okay, you will get 2833.7 kilojoule per kilogram. Okay, we got H2. Now we need to get S2. Okay, to get this S2, I think we need to use table A4. So at point 2 at the turbine exit, we have a pressure of 1 bar, and we also have enthalpy of 2833.7 kilojoule per kilogram. And I think you will need to do an interpolation to get S2. So we have 2833.7. Okay, I take the screenshot some of this table A4 to find out what is S2. So as we have H2 from the previous slide. So let me write it down again here. H2, I think 3.7, I think 7 kilojoule per kilogram. So if you look at this table at 1 bar, so this 2833.7 will be between this one. Okay, so temperature between 160 and 200. So try to do a simple interpolation to get S2. Okay, let me calculate it. You can do it yourself as well. If you are in front of your computer, you might use Excel to get a faster result, I believe. So you will get S2 7.7423 kilojoule per kilogram Kelvin. Okay, so we got all data we need to calculate the exergetic efficiency. So exergetic efficiency equal to W over H1 minus H2 minus T0 times S1 minus S2 times 100%. So you plug in all number that you have. So we have, so this one is, so this one is over M, right? Yeah, because this is specific. So the work, what we have here is 271.95 kilojoule per kilogram, and then H1 is 3105.6 minus H2 2833.7 minus T0. T0 we assume it is 298, and then times S1 minus S2. So S1 is 7.5308. S2 is 7.7423. So multiplied by 100%. Okay. So if you use an Excel to calculate S2, then you already have the number there. Then you can plug in the number that you have to this equation to get this epsilon. And let me calculate this one. I think you will get 81.2%. Okay. So this is showing an example to calculate the exergetic efficiency of a turbine. You can do the same method to estimate the exergetic efficiency of other components like compressor, pump, heat exchanger using appropriate formula. Okay, we have completed this chapter 7. So I suggest you to look at the example in the books, try to solve it yourself by looking at the solution. And then there are plenty of problem at the end of the chapter. So I suggest you to look at the problem, solve it by yourself. Don't looking at the solution. I know there are a lot of solution outside there, so you can Google it, or even you can ask different resource, different tool. But my suggestion again, to be successful in this class, try to solve it yourself. You can do several times, and then if you get stuck, then you can looking at the solution and try to understand how is it solved. Okay, thank you.